Let's see. So hello and welcome to another lecture of 2DM3. As usual, there's some arbitrary background noise. If you want me to turn it off, please let me know as usual. So I'm thinking today we'll do a quick review of what we've been talking about, but then we'll do some live coding with CalcCheck. So I do have the chat open here on this window. If you have questions or particular problems, please let me know. All right. So, there we go. So again, if the music gets loud, please just let me know. All right. So I want you to look at this mystery steps down here, right? PNP and then golden rule gets us to P or P. Does anybody want to take a guess on why that is? Why? What's going on here? Does anybody want to take a guess? Can somebody just say hello to me?
The music.
All right. So does anybody want to take a guess? What's going on here? Does anybody want to take a guess? What's going on?
I feel like since the first and the second element are both P, when you apply the golden rule, it's just P conjunction P equals P equals P, but that just turns to true. So you just kind of come back to just this.
Exactly. I'll just write out the details here. Let's make this a bit bigger so it can be visible. Control Alt Enter. Usual. So P and P. Oh, in this notebook, I don't have the golden rule. Let me go to a one on conjunction. Here it is. Boop. So let's put that in there. Oh, this is, excuse me for a sec, it seems like I'm not getting, my notebook seems to have died. Okay, there we go. Have to restart. Sorry. So this is just P equals P or P, and then we can just apply identity of true, which is, remember, we're doing identity stuff is implicit. All right. Okay, so it's when you say a few more steps, it can look a bit longer, and you can, if you decide to also ignore associativity, then you have to put in the parentheses and stuff. So it can get a bit longer that way. So I just wanted to show you some of these mystery steps to show, hey, by having implicit identity, implicit associativity, implicit symmetry, a lot of proofs can suddenly become shorter, right? So just like having precedence rules can make life easier, having identity and associativity and symmetry rules can make life easier. Okay. So I'll leave the other two for you, and let's consider other stuff today. All right. So as I said a moment ago, I really want to focus on doing some CalcCheck today, so live CalcCheck. So hopefully we'll do some of that. If you have particular theorems you'd like me to do, please let me know. So I've opened up the book you have on positional calculus. Is there any theorems anyone would like me to prove for you? All right, we can start anywhere and go from there. I just want to do some theorems in front of you. If no one asks, I'll just do the last theorem on the slide. So I'll do 342, contradiction, unless somebody says otherwise. Right, so let's prove this theorem. Let's prove that this is equivalent to false. All right. Well, the only thing you can do is apply golden rule, which says P equivals not P equivals P, not P. Okay. Well, this is a bit silly, right? Everything is nothing can be the same as its opposite. So if you recall, this is called definition of negation from equivalence, right? Here, I'll write it down in case some of you may have forgotten. This is x equivalent, sorry, it's L naught x is the same thing as x equivals false. That's what that rule is. Okay. Make sure we have no syntax errors right there. All right. So that's just false equivals P or not P. But wait a minute. You know that P or not P is the same thing as that's just the law of the excluded middle. Everything either is or is not, right? That's what the law of the excluded middle says. So just check that. All right. Sorry, forgot a space. Right there. This is why people don't always live code. It can be a bit tricky. Law of the why isn't that showing up? Tried EM. Why is this not showing up? I don't know why that's not showing up. Sorry about that. But it should be law of the excluded middle. Excluded middle. I should say false equivals true. And then just identity of that guy. And we get false. Okay, so I just wanted to show you some of these proofs as we're going along. If I do make some typos, I'll try to ignore them just for the sake of moving on. All right. So yes, let me know what else you'd like me to do. All right. So we talked about the unfold fold strategy, as I just tried to show a moment ago. All right. So here's a few more theorems. All right. The most notable one would be De Morgan. So let's try proving De Morgan. Let's go back here. Boop. All right. So we're saying it is not the case that, where's De Morgan's? It is not the case that we have P and Q. And our goal is just to simplify, right? We're starting off with the negation of P and Q, and we just want to simplify. How can we simplify this? Well, the only thing we know is to apply the golden rule, right? That gives us not P equals Q equals P, like that. Okay. So we talked about when proving these theorems, we should usually start with the more complicated side. So maybe just to show that heuristic, I should do that. So sorry for changing things, just to show you that. But anyhow, regardless, we can still apply the golden rule, and it will just give us not P and not Q equivals not P equivals not Q, right? So when you're proving a theorem, look at what's more complicated and try to start from there and move on, okay? So we'll notice right here we have two knots, so we can get rid of those two knots, all right? And how do we get rid of those two knots? Not P or not Q is the same thing as not P and not Q. Okay, well, what we can do is we can do not connection, all right? That's a theorem that lets us move them around. Not P and L not Q equivals just P equivals L not Q, right? And we get to move the knot to the other side of the equality. That's all that happens over there. And then the only thing we can do here is double negation. All right. And so that gets us to L naught P, L naught Q, equals P equals Q. Okay, so we're getting really, really close, but we're missing a central piece, right? So when you get stuck like this, one thing you can do is say, all right, I don't know how to proceed. And it's called burning the candle, starting from one side and going to the other side. So right here, it doesn't seem like there's any obvious steps. So rather than just stop the proof and say, oh, you can figure it out on your own, let's look at the other side. So the other side of De Morgan says you have the negation of P and Q, and the only thing you can do is apply the golden rule, and that will get you to I'll get you to the negation of P equals Q equals P or Q. Okay. All right. And notice where we're burning the candle from two sides, as it were. So let's make sure we have no typos. All right. We started here at this more complicated expression, right? And we're trying to get down to here, but on the way we got stuck. All right. We got stuck right here. And so we said, you know what, we don't know what to do. So let's start on the other side and work our way up, and hopefully we can get closer. Now, first thing you'll notice is we have a P equals Q and we have a P equals Q. So everything looks really, really good. So we're making fantastic progress. The only pieces we need to get similar are this P or Q, and then right here, not P and not Q. Okay. So one thing to do would be to say, all right, if we prove the other De Morgan's theorem down here, we're going to be good to go, right? But we want to prove the first one without reference to the second one. So this attempt didn't work. So the next thing to do, right, we got stuck. The next thing to do is to say, let's prove the whole thing is equivalent to true. So I have this thing, P and Q. Oh, no. Q. We try to prove the whole thing to be true. Oop. So this is not P equals Q equals. Actually, I guess I'll just stop. But I just wanted to show some heuristics. It's unfortunate I couldn't prove this right now in front of you. But yes, sometimes these things require a bit more time and subtlety. So I'll leave De Morgan's for now. But I can come back to it if someone insists. So I'll just move on. And maybe if I have time, I'll come back and I'll work out through the details. All right. So De Morgan's is just on how you can throw the negation over ands and ors, and it turns them into the other one, just like how for maximum and minimum, subtraction flips the two, right? The subtraction of a maximum becomes a minimum, right? So very similar laws, but these ones are for De Morgan's. Some of you were asking about whether you need to know rigid matching or not. So you can try to prove De Morgan's with P's and Q's using golden rule with P's and Q's, but as a fun exercise, try to prove De Morgan's with P's and Q's using T's and U's, okay, and explicit substitution, and see how that goes. All right. So let's try proving another theorem. That one failed. Let's try proving strong modus ponens. Hopefully that one won't be as hard. All right. So sometimes these theorems they do require a bit of time and prep, and I wanted to try to show it to you on the fly, as it were, but that did not happen as I would have liked. Okay, so the only thing we can do is apply the golden rule. Then we can apply identity of equivalence to get us to Q equals P lor equals P. If I'm skipping some steps that make things confusing, please let me know, and I'll go a bit slower. So we'll apply distributivity of or over equivalence, and that will get us to Q equals P or Q equals to P or P. Okay. And we will apply idempotency or that will get us to Q equals P or Q equals P. And this is just the golden rule again. All right. Okay. So sometimes things work out nicely, sometimes things don't. in comparison to De Morgan's, which involves ands, ors, and negations and equivalences. So it has a lot more moving parts. This theorem, strong modus ponens, only involves ands and equivalences, and so it has less moving parts. Not a lot of rules we can apply. And so golden rule to unfold, and then golden rule to fold up again. All right. Here's an acute theorem called replacement. It looks very, very, very similar to Leibniz, right? Remember, Leibniz says if two things are equal, you can substitute equals for equals. So if P is equal to Q and R is equal to P, then that's the same thing as P is still equal to Q, right? How Leibniz had two things being equal. But now, instead of R equaling to P, well, we know P is the same as Q, so we can say R equals Q. Okay, so replacement is very in the flavor of Leibniz, and later on we'll get to theorems 3.84, which are substitution and replacement theorems, which try to axiommatize Leibniz and our consequences of it, so-called contextual rules. Okay, look at the formula and give us some contextual information. All right. I just want to point out that and distribute over equivalent, semi-distribute over equivalence. So when you try to throw it over, you have an extra piece lying at the very end. Exercise and distribute over equivalence. So if you can decode what that means, you'll find out. So here's a definition of equivalence that you'll see in most other classes, like someone mentioned Math 1CO3 earlier, or like Philosophy 2BO3, Introduction to Logic, or Mathematical Thinking, or Introduction to Computational Thinking. You'll see that equivalence means they're both true or they're both false. Okay, that's all right. Yes, over the Booleans, that's what it means to be equal. The way we've introduced it in this class is equivalence is symmetric, associative, for equality, it's transitive, has an identity rule. So we gave axioms about it. This one gives a low-level implementation from which the axioms could be proven. But unfortunately, classes that introduce equivalence like this usually treat equivalence as an abbreviation and not an operation in its own right. And then they call it mutual implication. So maybe we'll get to that later today. And then there's also, of course, inequivalence, which is obtained by negating the formula up here. So apply De Morgan's, not P and Q is not P. Sorry, no, you don't apply De Morgan's directly. But if you start here and apply De Morgan's, you should be able to get to that one, right? Fun little theorems to try out. We are going to, so hopefully we'll be able to get to do some Ladies and Tigers, or maybe some Knights and Knaves, or Alice in Puzzle Land for the midterm. So we thought we'd bring it up. This is the same formalization you saw last time. Exactly one of the signs on the door is true, and we formalize sign 2 in this longish way. So hopefully, as we encounter more operations and laws, we'll think of a more terse formalization of S2. So it's not really that important to understand all the details, but you should be able to. So before I said, when I first showed you this, you couldn't understand them, but now hopefully you can. You're familiar with the terms golden rule, zero, 332. This was mentioned as an important nameless theorem to remember. And of course, if a room has a tiger, then it does not have a lady. Okay, so hopefully we'll do some of those. I actually pulled up the Knights and Knaves here, so we can try doing some of that if you like. Does anyone feel strongly about doing some Knights and Knaves problems? I'm just curious. If not, we'll move on. Can I get a yes if anyone's interested, or a beep or a note? I am looking at the text notifications. Okay, I'll take your silence to mean you're not interested. Okay.
There were a lot of things in chat.
I'm not seeing anything in chat. I'm not getting anything at all in chat.
Can we check scenario G for a knight and a nerves?
Scenario G, yes. So scenario G is a bit involved. Sorry, you said a lot of people are texting, but I'm not seeing anything. 1 second. I'm not getting anything neither on my phone nor on my laptop. But I believe that people are texting, and maybe there's some technical concerns. So scenario G is about a number of people. As scenario G, so if you remember on the last slide, last lecture, we talked about trichotomy, and we said, hey, either for any two numbers, they're either equal, less than, or greater than. And so we said, okay, here, let me formalize it for you. So A says all of us are knaves. So A says A is a knave, and B is a knave, and C is a knave. Okay, so that's what we know about A. And B says, what does B say? B says exactly one of us is a knight. So B says something like this. So B says, let's remove that. Sorry. So B says either A is a knight, or B is a knight, or C is a knight. So if you remember last time, we talked about saying when you have an equivalence, P equivalents Q equivalents R, that means either one or all of them are true. And this is covered in the supplemental lecture notes. Just seeing here, somebody has notes. So this is covered in the supplemental lecture notes. It means either all or an odd number of them are the same. I'm just trying to see. Can somebody type in the chat? I'm just not seeing anything in that chat. Okay. All right. I see the chat now. Okay, so people have been talking. I unfortunately have not seen the chat. Apparently my system seems to have stopped. I apologize for that. But I do see the chat now. So yes, apologies regarding that. Anyhow, so P equivalents Q equivalents R means either one or all of these are true. So we talked about this at one point, I think, right here. Right, we said when you have a chained equivalence, then that means an even number of the arguments is false, or when there's an odd many of them, that means an odd many of them are true, right? So, so hopefully you remember this from last time, okay? So that's what we're going to do for the first part. Okay. So either one or all, but we're saying exactly one of us is a knight. So this says one or all of them. So we have to say, and it is not the case that A is a knight, and at the same time, B is a knight, and at the same time, C is a knight. Okay, so this is the way to formalize it. I gotta stop checking that. Okay, so here's one way to formalize this. It is a bit lengthy, so I'm not going to go into the details, but hopefully we'll get to chapter 3.6 maybe next time. And a nice way to solve this is to use replacement 384. You can do it without replacement. You can, but I feel replacement would be easier. The idea is when you have a conjunction, right? You use information you know here somewhere else. So substitution. So this is some of the theorems we'll get to later on. When you know that E equals F and you've used E in an expression, then you can replace it with F everywhere else. So hopefully we'll get to that later on. But you can do it without replacement as well. It's just a bit lengthy. So maybe we'll take it up in tutorial, okay, instead of in lecture. All right. So does anybody want me to do maybe a simpler one, or maybe let's move on since we're running a bit out of time. Just a reminder, equivalence is not the same thing as equality, right? So just in case anyone still has doubt, equivalence is associative, equality is conjunctive. Okay, how you read them matters. So unfortunately, sometimes students will think the golden rule lets them deduce P and Q is the same as P equivales Q, like because they're treating it conjunctively, like down here. So that's not the case. It is an associative operation, and you read this formula associatively. You do not read it conjunctively. Okay. If you decide to read it conjunctively, you must first pick a particular parenthesization and then go from there. So let me explain what I mean. So suppose we want to say P and Q equivales P equivales Q equivales P or Q, and we want to read this conjunctively, right? Well, the first thing is let's not change anything. So just reflexivity of equals. I'm not changing anything. And now I'm going to say, all right, I want P and Q to equivale P like that, equivales Q equivales P lower Q. Okay, so I just picked the parenthesization. Now that I've picked the parenthesization, now I can say, you know what? Equivalence is just equality on the Booleans. So I can say this is P and Q equivales P. This time it's in equals Q equivales P lower Q. Okay, so now notice this is true now, right? So you pick a parenthesization and then you can replace equivalences with equals if you decide. But as it stands, it must be read associatively. So you can't just treat it conjunctively without doing some preliminaries, right? So just a quick reminder on that. Someone asked, yes, the lecture is being recorded. I certainly wish it wasn't, because I did not prove a theorem earlier, and that's unfortunate. So that will haunt me for the rest of my days. Anyhow, let's move to, so as I mentioned last time, you can read the golden rule in many different ways. In particular, you can read it this way, right? The minimum of two things is P, precisely when the maximum of two things is Q, right? The minimum of two things is the first one, precisely when the second one is their maximum, okay? And this idea of using treating numbers as if they were Booleans is because and is like minimum and or is like maximum. They share many similar properties. Okay, ducks. In particular, this is one way to parse the golden rule. Notice we have an equivalence for Booleans and equalities on numbers. All right. Okay. So this was mentioned at the beginning, so let me just show that again. It's kind of cool. You start off here, you say golden rule, and then you get here. All right. So I'm just curious, who thinks this will type check by itself? Who thinks this will proof check by itself if I just enter that? Does anyone think this is just going to work? Hello, person who just came in. Who thinks this will proof check?
I don't think it will.
The cool thing about having a system at your hands is you can Control-Alt-Enter, and you can see it in front of you. So it timed out, right? Because there's too many combinations, right? Like it can try to simplify, and then it might not work, and so it can time out. So good guess to, I don't know who said it, but good guess to you, person. So if you do this kind of stuff on the midterm and you're like, oh, it's clearly obvious, you know, you just apply the golden rule 3 times. It's not a big deal. We can go all the way here. This is clearer. And then we can do idempotency. Okay. Okay, so this will work. But if you get a lot of timeouts during, for example, the midterms or the exam, and you're that can be considered a denial of service attack, and that can be a concern for academic integrity. Okay, so just to let you know about that. So hopefully just be careful if things are timing out repeatedly, try to split them up into more steps. All right. Please, so when you paste things into MS Teams, it does have an option for like languages, like programming languages, and you can pick like Haskell, for example, which is indirectly, CalCheck is based off of Haskell indirectly, and you can, pick Haskell and then paste your code in there, and it will look nice, right? If you use backticks, it will also format your code nicely. Please don't give us images. Images are not very helpful, and sometimes they're very blurry. And I can't copy paste your image to find out what's wrong and play with it. So please just type things up or copy paste them and give us that. All right. So today we're hopefully making it to implication, so that's neat. This first one, the definition of implication says P implies Q precisely when P or Q equivalents Q, and it looks very strange, all right? And the intent, again, if you think in terms of numbers, is that P implies Q is the same thing as less than or equal to on numbers, right? And for example, M is less than or equal to N on numbers precisely when the maximum of the two is the larger one, right? So M is at most N precisely when their minimum is M, right? So treating and like minimum and or like maximum can give you a nice a feel for these rules instead of making them seem strange and esoteric. And indeed, implication is an order on the Booleans. So let me get to that. Okay. So for the next midterm, you should be able to look at this bottom slide down here and list all of these theorems. If you're not comfortable with the word symmetry, associativity, idempotency, distributivity by now, I really recommend you read up on these. So these are things you should be familiar with for the next midterm, all right? So back to the definition of implication. You can define it in terms of maximum. So P is at least Q precisely when the maximum of the two is Q. P is at least Q precisely when their minimum is P. All right. Another way to read this implication is as stronger than instead of less than or equal to. So you can say P is stronger than or equivalent to, right? Just as you would say less than or equal to, right? The things that all the solutions to P are going to be contained in the solutions to Q. So Q has more constraints, P has more constraints than Q. And so in some sense, P has a smaller set of solutions, okay? Another way to read it is, of course, as at least as strong. And then this is what I mentioned a moment ago about how it's analogous to maximum and analogous to minimum. Hopefully in the next little while, we'll get to greatest common divisor and least common multiple. There's some notes on these down here, if you're so inclined. We may change these a little bit. Everything's up for change. So just some things to be aware about. And when you have implication in hand, inference rules can now take on a more familiar shape. Instead of having a bar above them, all right, so remember Leibniz had a bar above it, so we can change that ever so slightly. So just as you remember, an inference rule is like you've seen in elementary, 12 plus 7 equals 19. And then we wrote them like this as a fraction, and we put the name of the rule on the side. But when you have access, so this is meta syntax. It says if everything above the bar is true, right? If everything above the bar is valid, then everything after the bar is also valid, right? So for all substitutions of values for variables, in the conclusion C, you'll always get true, right? In the Boolean case. But now that we have access to the operation and, instead of having white space between the premises P1 all the way up to Pn, we can say, hey, it's a conjunction. And instead of having a fractional bar, we can have an implication. Okay, so that's really neat. Now that we have the sufficient language to talk about implications, we can actually write them in the object language, right, in our logic. Whereas the fractional notation is meta syntax, this implication is language syntax. So some languages, some logics don't have a notion of implication. They don't have a notion of conjunction. And in that case, you need to use the bar notation. So the bar notation is more general. All right. So I just wanted to mention that briefly. Okay. So again, by treating these as implications as less than or equal to, as order operations, as it were, P is less than or equal to the maximum of P or Q. All right, that sounds reasonable. The minimum of two things is at most the first one. It's also at most the second one. The minimum of two things is at most their maximum. Right? So all of these suddenly become trivial theorems, if you will. And again, so it helps to sometimes think of these in terms of numbers, just to get you started, or so I find. And of course, there's a bunch of useful results we can prove to get us comfortable with implication. The last one is really neat. The last one is called shunting. And the idea is if you have a chain of implications, right? So I have P, and P implies Q implies R. So I have P, and then I can get everything here. But everything here is I have Q, and I can get R. So right here, when I'm at the position of R, I already have P and Q. So at the position of R, I already have P and Q. If you think of and as being a record former, right? Like I have this thing and I have this thing in my hand. So like a struct or a product type. Then you'll see, and then you think of implication like function arrow, right? And then you realize shunting is the idea of taking a function that takes a tuple. It takes two things, right? So if I have a function that takes an A and a B and it returns a C, I can think of that as a function that takes an A and then it returns another function. All right. So this is called currying when you do it for programming. Right. So the idea of partially applying f on one argument, right? And then sometimes people call that. So this would be. So g of a is sometimes written f subscript a, right? Right, to indicate, hey, I've partially applied f to one argument. So I just wanted to mention that. Currying is very prevalent in programming, in functional programming languages, such as Haskell, for instance. In mathematics, currying is done implicitly by taking a function like this that takes a product and then subscripting it to get a function that returns another function. Right? Don't worry if you don't know what any of this means. We'll get to functions and product spaces later on in the class. So don't worry if you don't. Just trying to show you some cool things. All right. So we did talk about natural numbers right here. So the idea of natural numbers is you start off with 0. 0 is the smallest number, and then you just stack things on top to make newer numbers. Right. So this is called induction or inductively defined data types. So hopefully everyone did the homework by now and you know what to do there. This is all in chapter 12 of the book, I think. So for example, this factorial operation and examples about it can be found in chapter 12 if you're so interested. This problem on evens and odds was the homework. And let's see if we can show an example of what this looks like today. So I hope everyone remembers the inductive principle. And I just want to show an example. Put it somewhere here. So monus. Let's talk about this monus function. All right. All right. So let's see if we can do that. Okay. So when you're subtracting two numbers, right? You don't have access to the negative integers, right? We're only talking about the natural numbers. So you don't have minus, you have monus, right? Mona says if you have nothing, so pretend you have a bunch of books on the table and you want to take n books away from the table. That's what Mona says. Pretend you have books on a table and you want to take some other number of books from the table. If the table is empty, you have 0 books, and you try to take any amount from the table, what's going to be left over? There's going to be 0 on the table. The table's empty. You try to take stuff from it. The table remains empty. That's what the first one says. Okay. Okay. The second one says, if the table's not empty and you try to take nothing from the table, then the table remains as it is, still not empty. The last rule says, if the table's not empty and you take at least one thing, then the table lost one thing, and the amount of stuff you have left to take over is also reduced by 1. Okay. If my table has m plus 1 many things, and I want to take n plus 1 many things, then my table is reduced by 1, and the amount of things I want to take is reduced by 1. Okay. So here's the generic shape of an induction proof. So let's prove that if I have a table and I take everything off of the table, all right, so I have a table consisting of m books, and I take m books off of the table, then I have 0 books. All right. Now, usually when you perform a proof by induction, all right, you're trying to prove a theorem. We're trying to prove this theorem, all right? And rather than try to prove it for every instance of m, right? Is it true for 0? Is it true for 1, for 2, for 3, so forth, so on? That will take an infinite amount of time to do. So instead, we turn to the idea of induction, right? So imagine you're climbing up a ladder, right? And you want to say, you know what? The thing I'm proving is I can get to any step on this infinite ladder to heaven. I can get to any step. Okay. Then what you do is you say, all right, first I have to be able to get on the ladder, get on the first step of the ladder. So that's usually called the base case. I have to get on the ladder. And then wherever I am on the ladder, I should be able to reach up and get the next rung. Okay. So this is called the inductive step. So wherever I am on the ladder, I can reach up and get the next rung, and I can get on the ladder. So that means I can get to any step you want. To get to step 23, well, I know if I'm on step 22, I can reach up to get to 23. So let me just get to 22. To get to 22, I just need to get to 21, because we know if I'm on 21, I can reach up to get to 22. And so I can slowly work my way up to get to step 1. I need to be on step 0, and step 0, I can reach up to get to step 1. And how do I get to step 0? Well, I already said, hey, I can get on the ladder, right? So this is the idea of induction. And if you try to phrase it this way, it becomes an obvious observation or a basic observation. So let's try to prove m minus m is 0. So what's the goal here? Our base case is to show 0 minus 0 is equal to 0, right? That's what we're trying to show here. So notice I'm communicating my intent, and CalcCheck is checking my intent, right? I don't have to write that down. This is optional, so I can remove it, right? And on my side, I don't see explicitly what I'm proving, but CalcCheck knows what I should be proving. I think it's a good idea to always communicate your intentions at the very beginning. I think it's good for you, and otherwise you might make mistakes. So let's do that. So 0 minus 0, and we need to get to 0, right? And we can check our proof as we go along. All right. So the first thing to do is, notice question mark as usual does not prove anything. So 0 minus 0, the only thing to do actually is call on the definition, which says if you try to take from 0, you stay at 0. You stay at 0. Okay, so that was really easy. Now, what's our induction step? Well, we're proving that the successor of m minus the successor of m is equal to 0. So let's just communicate that. And indeed, what we think and what CalcCheck thinks are in alignment. And that's again with command correctness or proving programs correct. You communicate your intention using assertions, as it were. So let's do that. And there's only thing we can do, right? So we call on the definition there. Subtraction of successor from successor. All right. Let's just check on that. Yep. And we're still not done. So let's apply the induction hypothesis. So remember, we want to show the claim is true for successor of M. We want to get to the next rung, but we're already on the current rung, which is for M. So we get the induction hypothesis says M minus M is 0. So I can use that, and we're done. Okay. So I'm really glad we have some more time. So let's prove another theorem. So usually when you work with a definition by induction, so here notice there's only one variable. So I did induction on that one variable. When there's multiple variables, you usually look at the definition and say, where is it being defined on in the definition? Is it being defined on the first one, the second one? Where is pattern matching happening on the in the definition? And then you follow that. So let's try to prove this theorem called subtraction after addition. All right. If my table has at least n things and I take away n things, then my table has everything else besides the original n. Okay. Since there is an addition here, and we know addition is defined on the first variable, so right here, definition of addition. All right. Notice how it's defined on the first argument. All right. The second one is left alone. Right. So because of that, it's a good hint we should do induction on M. All right. So let's try to prove that 0 plus n minus n equals M. So let's try to prove that. Sorry, equals 0, because we said that's what it will be. All right. So 0 plus n minus n. Well, the only thing to do is to apply the left identity of addition to get the n minus n. But wait a minute. How convenient. That's the previous theorem we just proved, right? Self-cancellation, all right? So let's get that theorem there. Self-cancellation of subtraction. And so we're done the base case proof, right? So that's all done. And then next we go to the induction step. The induction step, right? Well, what do we need to prove for the induction step? We need to prove the same thing, but now we have a suck here, all right? So let me just make a little scratch pad. So we're trying to prove suck M plus n minus n equals suck M. This is what we're trying to prove. Unfortunately, if you look at our rules, this one involves only 0 on the left. This one involves a suck on the left. So this is a rule we can use, but it only has a 0 on the right, so can't use it. We want to. So the only one that has a suck and a variable on the right is the last one. But the last one requires a suck, and that's not what we currently have. So how do we introduce a suck? Well, we can say, let's look at n. Is n 0 or is n suck? And to look at the shape of n, that's what induction lets us do. So let's do another one. So by induction on this time n. Okay, so we'll do induction on n. All right. So let's, oh, sorry about that, bye. So we have a base case that we need to tackle, and then we have a new induction step that we need to tackle. Right. So when you have one induction proof inside another, this is called nested induction. Right. So the base case, and so let's communicate what we think that is. It's going to be exactly this formula, but we replace every n with a 0, because we're doing induction on n. All right. So we have suck m plus 0 minus 0. Okay. And we want to turn that into just suck m. Okay. Well, we know we have a right identity of addition, so let's apply that to give us suck m minus 0. All right. And then right here, we need a right identity of subtraction to get rid of this one. Right. So we can prove that as another theorem. All right. right identity. Okay, so I'll just leave that there, right? Not too difficult to prove, hopefully. And then we'll say right identity of subtraction to make progress right here. Okay. It seems I've run out of time, but hopefully I've shown you what's going on. And this is the idea of nested induction, having one inside the other, and hopefully we'll get to that in the exercises this week. Anyhow, hopefully you had a good session, and yeah, have a terrific Tuesday. Bye.